Now let's do one example for a regeneration cycle. Steam enters turbine at 8 megapascal, 480 Celsius. Part of the steam leaves the turbine at zero point 0.7 megapascal. The rest of the steam leaves the turbine at 0.008 megapascal. Saturated liquid water leaves the open feed water heater. W dot cycle is equal to 100 megawatts. First one is to sketch the whole process on a T versus S diagram. Second one is to look for the efficiency. And part 3 is to look for the total mass flow rate m.1. I believe you have noticed that all the numbers we give you in the past 3 examples are exactly the same. For example, 8 megapascal, 480 Celsius, zero point 0.7 megapascal, zero point 0.008 megapascal, and 100 megawatts. The reason why we always give you the same conditions is because you can do a comparison. So for example, the first one we had was a Rankine cycle. The efficiency was about 37%. And then under the same conditions, we changed the cycle to reheat cycle. The efficiency went up to 40%. And now today, we are going to change the cycle this time to regeneration cycle under the same conditions. And let's see if the efficiency can go above from even 40%. First thing first, we need to sketch the process on a T versus S diagram. We have a vapor dome first. Sketch a constant pressure line. We should have 3 of them because we have 3 pressures. Okay, so the top one is at 8 megapascal. The middle one is 0.7 megapascal. And the bottom one is 0.008 megapascal. First thing, locate point number 1. How do we do that? We've done that several times now. We go to table A3. We start from P1, which is 8 megapascal, and that is equal to 80 bar. And from here, we can find the corresponding saturated temperature. We call it Tsat1, and the value is 295.1 Celsius. And we know our actual temperature at T1 is 480 Celsius, which is even higher than Tsat1. So our conclusion is 0.1 must be superheated. However, is that enough for us to fix the location of point number 1? No, because point number 1, for example, can be here, and then 1 to 2, which is the steam turbine. So 1 to 2 goes straight down. Number 2 will end up as a mixture. That's case number 1. Case number 2, can number 1 be here? So number 2 will become saturated vapor. Or even further to the right. Yes, you have 3 possible solutions. And for this case, you have even more possibilities. So what do we need to do? We need to find a reference line. In this case, you need 2 of them. The first one is this one. This point we call point 2G. And then we need another reference line, which is cross this point. Okay, we call this point point 3G. So the x-coordinate here is S2G, and x-coordinate here is S3G. What you need to do is to compare S1 with S2G and S3G. So for example, if S1 is less than S2G, you must put point 1 to the left of point S2G. If S1 is between S2G and S3G, you must put point 1 between the 2 reference lines. And if S1 is greater than S3G, then you must put number 1 to the right of point S3G. So we need to look for S1, S2G, and S3G. Let's start from S1. How do you look for S1? We know point 1 is superheated, so you have to go to table A4. Two inputs. P1 is 8 megapascal and T1 is 480 Celsius. And from the table you can find S1 and also H1. Okay, so now we have S1. Next, we look for references S2G and S3G. How do we look for S2G? What do we know about point 2G? We can take a look. Point 2G is on the pressure line, 0.7 megapascal, so we know the pressure. If you start from pressure, you go to table A3. Okay, since I am at table A3, I might as well also write down HF and HG. So now we found our first reference as 2G. Okay, then we look for our second reference. Our second reference is S3G. How do we look for S3G? We do the same thing. We repeat table A3, and the pressure of 3G is equal to P3, which is 0.008 megapascal. And from the table we can find SF and SG. And again, we might as well write down HF and HG. Okay, so now we've found the other reference line. So now let's take a look S1 versus S2G versus S3G. So we can say that actually S1 is even less than S2G. S1 is 6.6, S2G is 6.7, so S1 is even smaller than S2G. So what is our conclusion? Point 1 must be to the left of point 2G. So now we go back to our diagram. We put number 1 to the left of point 2G. So number 1 has to be somewhere here. It has to be superheated, so it must be to the right of the vapor dome, and it's on 8 megapascal line. Okay, so now 122. What is 122? If you forgot, we can go back to our analysis. 122 is the steam turbine, and the mass flow rate is m.1, so that's black. And after you reach number 2, you separate them. You separate the water vapor into two streams. The first one is 226, the second one is 223. Okay, so let's do this. 122, go straight down and use color black because the mass flow rate is m.1. And after point 2, you separate the water vapor into two streams. One of them will just be hot, it will just leave the turbine. So it's going to be red to the left. And then the other one will be blue. What we'll do is to continue going through the rest of the turbine, so going straight down furthermore. And then that is your number 3. And 3 to 4 is the condenser, so moving to the left. Condenser. Number 4 is point F. And then 4 to 5 is the pump up the pressure. So go straight up, 4 to 5. And then 5 to 6, moving to the right along this constant pressure line. And 2 to 6, same thing along the constant pressure line, moving to the left. Blue meets red at point F. And for point F, we use color black because the mass flow rate becomes m dot 1 again. And then 6 to 7, go straight up. 6 to 7, go straight up because it's the pump. And then 7 to 1, the boiler. That's it. So now you can see the most difficult part in sketching the diagram is to locate the location of number 1. Once the location of point number 1 is fixed, everything is fixed. Okay, so that's part 1. Sketch the process on a T versus S diagram. And then we move on to part 2, efficiency. And what do we need to find efficiency? Let's take a look at the efficiency equation we derived, number 6. And take a look at the right-hand side. What do you need? Enthalpy of every single point. Once you have enthalpy of every single point, you can solve for efficiency very easily. Okay, so let's start from H1. What is H1? We actually found H1 is right here. So let's just copy. The value of H1 is 3348.4 kilojoule per kilogram per Kelvin. That's H1. Next, we need to find H2. Okay, what is the phase of number 2? You can take a look. Number 2 is within the dome, so it is a mixture. How do you look for the enthalpy of a mixture? You have to have quality. And how do we find equality? We can find equality from entropy. So we've done this method several times now. I hope you can do it easily at this moment. X2 is equal to S2 minus S2F divided by S2G minus S2F. We have S2F, S2G. We found those two earlier, S2F, S2G. Right, you can see. And the only thing I don't have right now is S2. But take a look, 1, 2, 2 is a vertical line, so they must have the same x coordinate, meaning S1 must be equal to S2. And I do have S1, which is right here. Okay, so now you can just plug in all the numbers, and our solution is 0.9895. That's x2. And now, finally, I can find h2. h2 is 1 minus x2 times h2f plus x2 times h2g. I have quality x2. I also have h2f, h2g. We found them from earlier, right here, h2f, h2g. So we just plug and chug. Our solution for h2 is 2741.8 kilojoule per kilogram. That is H2. Next one, H3. What's the phase of number 3? Let's take a look. Number 3 is within the dome, so number 3 must be a mixture. So again, we need to first find quality x3, and be careful here because x3 is not equal to x2. The only thing you can get out of a vertical line is they have the same x coordinate. In this case, that is entropy. It has nothing to do with constant quality. Quality is not constant. X2 is not equal to X3. Okay, so the equation is S3 minus S3F divided by S3G minus S3F I have S3F, S3G from earlier. You can see they're right here. So the only thing I don't have right now is S3. But let's go back to the diagram. 1, 2, 2, 2, 2, 3 is a vertical line. S3 must be equal to S2 and must be equal to S1. So we can change S3 to S1. And I do have S1. So what you do here is just the plug and chug. Solution for x3 is 0.7944. And then finally, you can look for h3. The equation is the same as before. 1 minus x3 times h3f plus x3 times h3g. And we have every one of them. We found h3f and h3g right here from the table earlier. So now plug and chug. Our solution for h3 is 2082.9 kilojoule per kilogram. So that is H3. Next one, we look for H4. What is H4? Let's take a look. Point 4 is point F at P3, which is 0.008 megapascal. So H4 is essentially equal to H3F, and we do have H3F. H3F is right here. So I have H4 already. Okay, next one is H5. Okay, H5. What is H5? Let's take a look. Okay, 425 is the pump. If it is the pump, we always use the same equation. Okay, W dot pump, which is 425, over M dot is equal to, from first law, we know this is H5 minus H4. And then from our other equation, we have W dot pump over M dot. Oh, here it should be M dot. M dot. What is the mass flow rate for 425? That is blue, so the mass flow rate should be m dot 3. And same thing here, m dot 3. It is equal to w dot control volume work, 425 over m dot 3. And from earlier, we know the equation is integral nu dp from P4 to P5. And from here, they must be equal. So H5 minus H4 must be equal to integral P4 to P5 times nu dp. And again, we do the same thing. From 4 to 5, what is the phase of the liquid, of the water vapor? 4 to 5, you can see it is to the left side of the vapor dome, so everything is liquid. If it is liquid, density must be constant. And the inverse of density is nu, so nu must be constant. If nu is constant, we can take it out. And once you take it out, you can give it a subscript, and we prefer to call it nu, which one? Nu 4 or nu 5, doesn't matter, they're equal. But we prefer to call it nu 4 because nu 4 is equal to nu f at 0.008 megapascal, which is easy to find from table. We call it nu 4, and what is left is P5 minus P4. So from here, we can easily find H5. H5 is equal to H4 plus nu 4 times P5 minus P4. Okay, so now let's take a look. We do have H4, P4 and P5. They are very easy to find. You can just go back to the diagram. What is P4? Pressure of number 4. Number 4 is on 0.008 megapascal line, so P4 is 0.008 megapascal. What is P5? Number 5 is on this line, so the pressure is 0.7 megapascal. P4 and P5 are very easy to find. And next, we just need to find nu 4. How do we look for nu 4? We do the same thing. We go to table A3 and we start from P4. P4 is 0.008 megapascal, which is 0.08 bar. And from the table, we look for nu F, and that is our nu 4. Solution is 1.0084 times 10 to negative 3. Unit is cubic meter per kilogram. So now I have everything in the right-hand side. I can easily find H5. Okay, let's plug in the numbers. Here, be careful when you plug in numbers, make sure you use SI unit for every parameter in the right-hand side. H4, 173.88 times 1000 to convert kilojoule to joule, plus 1.0084 times 10 to negative 3, SI unit already, multiplied by P5, which is zero point 0.7 megapascal, so times 10 to the 6 to convert megapascal to pascal, minus P4, 0.008 megapascal, so times 10 to the 6. Again, the solution for H5 is 174.6 times 10 to the third with SI unit, which is joule per kilogram. And then one more step, that gives you 174.6 kilojoule per kilogram. So this is how you find H5. And next one, H6. Let's take a look. Where is number 6? Number 6 is actually point F at which pressure? At 0.7 megapascal, which is P2. So H6 is essentially equal to H2F. And do we have H2F? Yes, right here. We do have H2F, and that is our H6. H6 is equal to H2F. Okay, and then the next one is H7. H7. Okay, how do we look for H7? Let's take a look at diagram again. Okay, 6 to 7, that's another pump. And we always use the same method for a pump. So we just repeat what you did for number 5 again, this time to look for H7. Okay, so W dot pump. This time 6 to 7, the mass flow rate is M dot 1 because it's black. And then it is equal to 6 to 7. So that is equal to H7 minus H6. The bigger one is number 7, the smaller one is number 6. So we use the bigger one minus the smaller one. This equation comes from first law of thermodynamics. And then we do the same thing. The second equation is m dot p over m dot 1 is equal to, this is the control volume work for process 6 to 7, divided by m dot 1. And we know this equation can be calculated by integral nu dp from P6 to P7. And then those two must be equal. So H7 minus H6 is equal to integral nu dp, P6 to P7. And again, 6 to 7, take a look. What is the phase? 6 to 7 is to the left side of the vapor dome, so it's liquid. If it's liquid, we can always assume the density is constant. So the inverse of density, which is specific volume, must also be constant. So we can take nu out of it. If you take nu, the integrand, out of it, what's going to happen? You have to give it a subscript. You can call it either nu6 or nu7, and we prefer to call it nu6 because nu6 is equal to nu-f at 0.7 megapascal, which can be easily found from the table. Okay, so we take nu6 out of the equation. And what is left is P7 minus P6. So now H7 can be easily found. It's equal to H6 plus nu6 multiplied by P7 minus P6. Okay, H6, we already found this one. And P6 and P7, let's take a look. What is P6? Number 6 is on 0.7 megapascal line, so P6 is 0.7 megapascal. And number 7 is on 8 megapascal line, so P7 is 8 megapascal. So P6 and P7 are very easy. And then the only thing we don't have at this moment is nu 6. How do I look for nu 6? Do exactly the same thing as what we did for number 5. So we go to table A3. We start from the pressure P6. And what is P6? P6 is 0.7 megapascal, which is 7 bar. And you go to the table, you look for nu F. And nu F is your nu 6. Okay, and from the table, it tells you the value is 1.1080 times 10 to negative 3 cubic meter per kilogram. So that's nu 6. Now I have everything to find H7. And again, use SI unit when you plug in the numbers. Okay, H6, the value of H6 times 10 to the third SI unit plus nu 6. SI unit already multiplied by P7. What is P7? Let's always go back to the diagram so you can always find everything you need. P7 is 8 megapascal. 8 times 10 to the 6 minus P6. We have P6, which is 0.7 megapascal. So now the final solution for H7 is 705.3 times 10 to the third. And it must have an SI unit, which is joule per kilogram. And then we do one more step, that is 705.3 kilojoule per kilogram. Okay, so now we have found everything from H1 to H7. Efficiency now can be easily found. The equation is this one, H1 minus H2 plus 1 minus y times H2 minus H3 minus H5 plus H4 minus H7 plus H6 divided by H1 minus H7, and y is equal to H6 minus H5 divided by H2 minus H5. So now I have everything in the right hand side, and then you just do plug and chug. Your solution is 0.425. So now do you see the efficiency actually goes up? In the first Rankine cycle example, the efficiency was 37%. And then we moved on the reheat cycle, the efficiency was 40%. And now finally we're at a regeneration cycle where the efficiency is even higher, it's 42.5%. Okay, and then we can go to part 3, mass flow rate. Mass flow rate m dot 1. How do we look for a mass flow rate? We always do the same thing. We start from W dot cycle over m dot 1, and we derived this equation before. It is h1 minus h2 plus 1 minus y times h2 minus h3 minus h5 plus h4 minus h7 plus h6. So now let's take a look. Okay, don't forget y is still a function of enthalpy. h6 minus h5 over h2 minus h5. So I have y. I have everything in the right hand side. I also have W dot cycle, which is given as 100 megawatts. The only thing I don't have is m dot 1. One equation with one unknown. You can easily find the value. Just be careful when you plug in the numbers, make sure you use SI unit. So your solution is 89, and the SI unit is kilogram per second. Okay, that's the example.